Good afternoon, ladies and gentlemen. First of all, I would like to thank the organizers, particularly Ahmed Annawi and Yusuf Zaz for the kind invitation to share our recent results here. So as you can see from the slide, the title of my talk is Stable Perovskite Solar Cells by Compositional and Interfacial Engineering. You will realize immediately the importance of this technology and why we are working on stability of this material. So this is my email address, and my affiliation is EPFL, and I have two other affiliations, King Abdul Aziz University in Jeddah, Korea University as a world-class university professor. So during my talk, whatever questions you might be having, please send me your queries. I try to respond to you within 24 hours. So with that one, I just want to share our building. This is our campus. It's a really beautiful campus. On this side we are having a lake, and the other side we have a beautiful Alp mountains, and from our place going to mountains is really 15 minutes job. So this is our learning center. This is very unique architecture. It's like a cheese, a Swiss cheese on the top of the roof. This is our Congress Center. This is one of the best in the world. It can accommodate 5,000 people at a time, and the seats can convert into a banquet hall. Now I come back to the topic. So if you look at the today's status, perovskite solar cell efficiency has increased from 3.8% in 2009, and today we are 25.2% efficiency. How does it compare with respect to the existing technology? That's a silicon solar cells. That's a 26.6% efficiency. Silicon solar cells, they have an extremely stable performance over 25 years, but the problem with the perovskite solar cell stability is missing. So our focus, and the whole world is focusing, how to increase the stability of the perovskites by either compositional engineering, that's what you will see in my presentation, and interface engineering of these materials to increase the stability of this new technology. So if you look at the perovskite solar cell configuration, it's a very simple configuration. Next slide you will see the processing protocols. But to give you a nutshell, you have 3 layers, electron transport layer. This can be titanium dioxide, or it can be a tin oxide. Now then we deposit perovskite, that's a absorbing layer. We have a whole transporting material. These are the 3 main layers which we are working. So in our group, we are modifying the ETL layer, electron transport layer. Also we are working on the whole transporting material, and also changing the perovskite absorber composition. So these are the 3 highlights which I would like to talk. Probably the last topic, development of charge transporting materials, I may not have a time, but these first 2 sections, interface engineering, compositional engineering of perovskite layers, I try to explain as much as possible. Now I come back to the perovskite. What is perovskite actually? The perovskite is a mineral which has this type of structure. It's called a 3-dimensional network material. It has a ABX3 configuration. A is typically a monocation. It can be an organic cation, or it can be organic cation similar to methylammonium, or it can be formidinium. So these are the organic cations. B is an inorganic metal, 2+. It can be lead, tin+, tin 2+. And X is a halide, can be bromide and chloride, iodide. You can see the beauty of these materials. You can change the band gap of these materials by changing the halide, iodide to chloride, chloride to bromide. You can tune the properties, and you will see in few slides down beautiful colors from the yellow to red to black. You can also tune these properties of this material by changing the A cation, for example, cesium to formidinium, from 1.65 band gap to 1.48 or 1.5 the band gap. So since you have a cation changing, you can change the band gap, and by X halide also you can change the band gap. This gives you very good opportunity to tune your materials. What is so beauty of these materials? I highlighted here the 3 very take-home messages. The strong light absorption in the visible region. The band gap is important, but the absorptivity of the material is very important. So the perovskites, they absorb very strongly. Therefore, the required thickness of the perovskite is few hundred nanometers. How does it compare with the silicon solar cells? Silicon solar cells, you need at least 200 micrometers, and here what we need is 500 nanometers is sufficient to absorb all the light in the visible region. So that's a very strong message, strong light absorption by this material. The second, I already discussed a tunable bandgap by changing the halides, by changing the cations. And the third important message of this material is a small excitation dissociation energy. So if you take any material, organic, when you excite, you create a ion pair. This is exciton. And this binding energy is quite large in most of the materials. Fortunately, in perovskites, this energy is typically below 20 millielectron volts, which at room temperature, there is a discussion in the community. By the moment you shine the light, are we having a ion pair or the field carriers? Most likely, because of such a low binding energy, the moment we shine the light, we are having a free carriers in the material, and these carriers, they travel in any direction because the perovskite is a ambipolar. It can transport positive charges, it can transport negative charges. It's a ambipolar. So since they don't have the directionality, at the interfaces you collect these charges by selective contacts. At one side you put the electron transport layers where you tune the conduction band of the ETL layer with respect to the LUMO of the perovskite. In another side you put the whole transporting material where you align the HOMO of the perovskite with respect to the HOMO of the whole transporting material. So as I mentioned, this is a panchromatic material. It absorbs all the visible light from 400 to 820 nanometers, has a strong visible the emission coming in the band edge. And if you look at the onset, the onset is comparable to well-known material like gallium arsenide, showing so you have a very low trap density in these materials. So now come back to how you make these perovskite solar cells. I have just sketched here, and this work you can find in Sustainable Energy Fields. It's online. So what you do is you take your conducting glass substrate and you deposit a very thin layer, 25 nanometers of blocking layer of based on the TiO2, followed by mesoporous TiO2 layer around 50 to 100 nanometers. You sinter at 450 degrees, and then we deposit the perovskite, sinter at 120 degrees temperature. Then we deposit whole transport material, followed by the gold contact. And in the laboratory cells, they typically look like this one. And in the electron microscope, you can see this is a TiO2, which is typically around 50 to 100 nanometers thick. The perovskite is 500 to 600 nanometers. Depending on the solvent engineering, this I will take, if somebody is interested, I will discuss later how to grow this perovskite. But just consider that we are having 500 to 600 nanometers perovskite layer, and on the top we deposit whole transporting material, gold is a contact. And this type of solar cell gives you typically in our laboratory close to 22% efficiency. So that's measured in our lab, and these cells were sent to Newport in February, and there they measured 21.8 plus or minus 0.7, showing that our laboratory measurements and our system is consistent with the international laboratories. So this is a certified efficiency which we got from the Newport, 21.76 plus or minus 0.7. So as I mentioned that you can change its colors, and here you can see from the red to yellow. In between you have a dark purple and dark black color. So this is by changing your halides. And this module level between 6 by 7, we get close to 17% efficiency. So this technology you can also print on a plastic substrates, and you can also get very high efficiency. So these are the cells made by printing in our laboratory, typically 8 by 5 centimeters. So we are having this printing technology as well. Now we come back to that's a state of the art in our lab. In Korea, they have reported 25% efficiency. But the problem with the perovskite solar cells, as I mentioned, this is the stability. How do we increase the stability? So in our lab, what we are trying to do is combine the beautiful properties of the low dimensional perovskite. So I come back to what is low dimensional perovskite. So if you take our normal perovskite, that's a infinity, n equals to infinity, where the cation fits into the cavity by using the Goldsmith tolerance factor. So this forms a 3-dimensional perovskite. Now, if the cation, A cation, is bigger than the organic cation which I mentioned, 3-methylammonium and formidinium or cesium, then you slice into low dimensional perovskites that can be like a single sheet, or it can be 2 sheets, it can be 3 sheets by using this type of cations. Now, you can see the beauty of the 3-dimensional perovskite, which absorbs the whole visible region as I mentioned, but the drawback of this material is instability. And now you see the 2-dimensional perovskite, they are extremely stable because of these hydrophobic cations, but the drawback is they absorb only a very small portion of the visible light between 400 to 500 nanometers. So now the idea is combining these two 3-dimensional perovskite on the top, by putting the 2-dimensional perovskite on the top of 3-dimensional perovskite. That's what you see, what we call interface engineering. So now here is the cell. What we have done is we have taken the 3-dimensional perovskite and we deposited the 2-dimensional perovskite on the top. They look really beautifully green because if you take the pure 2-dimensional perovskite, that's the formula is phenylethylamine. So let me just go back. The cation which we are discussing is this one, phenylethylamine. This is the cation. When we put this cation, you form this type of absorption spectra. The emission spectra is consistent with the luminescent, and if you look at these cells, by naked eye, you can find out immediately that you have a 2-dimensional perovskite on the top of 3-dimensional perovskite. So if you look at one by one absorption spectra, the black is pure 3-dimensional perovskite, the green one is a pure 2-dimensional perovskite, and the red line shows that the absorption spectra of 2-dimensional perovskite deposited on the top of 3-dimensional perovskite. So the spectrally you see small differences, but if you look at the XRD spectra, so this is pure, the green is again pure 2-dimensional perovskite. Take this peak around 5, that's a characteristic fingerprint of the 2-dimensional perovskite. The black line, this peak is a characteristic peak of the 3-dimensional perovskite coming from this black line. Now, by combining 3-dimensional and 2-dimensional perovskite, you see the presence of 2-dimensional peak and presence of 3-dimensional peak. That's the XRD analysis of this material. Now, other direct evidence comes from the luminescence properties. Since now we have a 2-dimensional perovskite on the top of 3-dimensional perovskite, now you can excite, you can interrogate this material by shining from the top side, or you can excite from the bottom side. Since now we have put only the 2-dimensional perovskite on the top, you can see by exciting from the top side, you can see the presence of a peak which is coming consistent with the absorption spectra of the 2-dimensional perovskite, which is around 520 nanometers. Since the thickness is close to 60 nanometers, so the light is not penetrating, you can see very small blip coming from the 3-dimensional perovskite. If you take a reference sample and you do the shine from the top side, you don't have a presence of this 2-dimensional perovskite, you see the presence of pure 3-dimensional perovskite. These two samples, however, you can excite from the bottom side, they are overlapping. So this particular experiment clearly demonstrates the presence of layer by layer in your solar cell. So we have a 3-dimensional perovskite followed by the 2-dimensional perovskite. Fine. What is the importance of this material? So if you look at this is the UPS data. So the band energy diagram is built based on the UPS data. This is your 3-dimensional perovskite. The HOMO level of the 3-dimensional perovskite is well aligned with the 2-dimensional perovskite. So there is no barrier to extract positive charges from the 3-dimensional perovskite into the hole output material. However, if you look at the LUMO level, this is significantly higher than your 3-dimensional perovskite. What happens, the electrons which are generated here, so they are driven towards the ETL side and reducing the recombination at this interface. How do we know that this is happening? Take the IV characteristics at blank without this 2-dimensional perovskite. Look at the VOC, that's open circuit potential 1.09. By putting this extra passivation layer, or you can call also reducing the recombination, you can see the increase in VOC from 1.09 to 1.14. So this is a direct evidence for us to show that by putting this 2-dimensional perovskite, we are reducing the recombination at this interface. Fine. What is the importance of this 2-dimensional perovskite on top of 3-dimensional perovskite is shown based on the stability measurements. So the solar cells here, what we are having is the 3-dimensional perovskite and 2-dimensional perovskite solar cell. That's a red line. So the black lines are pure 3-dimensional perovskite. So the experimental conditions are the open squares are measured under argon atmosphere. So 800 hours they are extremely stable. and then the filled circles are encapsulated but measured under outside conditions. So they are overlapping, but in both the cases, we are having a two-dimensional perovskite on the top of three-dimensional perovskite. And if you look at the black lines, that's not the case. It's a pure three-dimensional perovskite. The stability is decreasing even though we encapsulate it. Within first 400 hours, the stability is decreasing significantly. However, if you put under argon conditions, it's relatively more stable. So the take-home message, so we have developed layer-by-layer deposition technique to enhance the stability of the perovskite, three-dimensional perovskite, by putting the two-dimensional perovskite. So this is based on phenylethylamine cation. So since we are chemists, and just to motivate the chemists, this is not the end of the world. Then this opens you enormous opportunities to tune your material. Phenylethylamine is one cation we have tested. So we don't know exactly how this two-dimensional perovskite is aligned on the top of three-dimensional perovskite. It can be a parallel, it can be perpendicular, but the required directionality is a perpendicular because of the extraction of the positive charges through the air bones. So, but however, in our case, we have taken 3 more new cations. So this is a reference sample, pure three-dimensional perovskite. The efficiency is 20% efficiency with 1.09 volts. That's a black line. Now we change the phenylethylamine by substituting the fluoro in the 4th position. It's called fluorophenylethylamine. You can see the VOC increased from 1.09 to 1.13, and the efficiency increased 21% efficiency from 20. That's a blue line, IV characteristics. And now we have developed another cation. This work is unpublished. We are going to submit this one. So we have taken a 5-fluorobenzylethylamine, and that gives you enhanced VOC compared to your pure three-dimensional perovskite from 1.09 to 1.15, and then the efficiency is close to 22% efficiency. And the beauty of this material is, if you look at the pentafluoro, the stability of up to 1000 hours, extremely stable performance compared to the fluorophenylethylamine, compared to three-dimensional perovskite. So this is the way we are trying to improve the stability by incorporating these interfacial layers. So we have another interesting study which is just published. It's online. We didn't get any page number, but the passivation of this perovskite by putting different passivating agents. So one of the passivating agent is a amorphous silicon dioxide. So the concept here is, this is a bulb. At the interfaces, you may be having traps. So these traps, we want to coordinate these traps by putting the agents, that's a passivating agents. You will see in the next slide what are the passivating agents we are using. This is PHPS. This is a silicon compound. When you react with the perovskite, it forms amorphous silicon oxide on the top of the perovskite. It's a very thin layer. You cannot see by even SEM image. It's a very thin layer. However, you can see the presence by different techniques. So what is happening here is, in the bulk, this is your bulk perovskite, and it's a purely N type of material. By surface passivation of this particular silicon oxide material, and we are changing the Fermi level. So what happens is, now you have bended the band, and this way you extract positive charges more efficiently at the interface, and then the electrons are going other way around. And this also gives you similar to 22% efficiency as I reported before. So this is the IV characteristics, 22.1% efficiency with the passivating agent, and without you have a 20.5% efficiency. So these are the some other characterization techniques to prove that this is passivating, and you can see the increased luminescence intensity, and the carrier lifetime is also increasing by putting this passivating agent. It also gives you enhanced stability as shown here. This is with the passivating groups like a passivating silicon dioxide, and this is without a passivating agent. So this enhances the stability as well. So you can do the very crude test. So this is the perovskite solar cell encapsulated with this passivating agent completely on top of this perovskite solar cell. This is a blank without any passivating agent. You dip into water. This is the initial data of both cells. Putting into water after the passivation, the efficiency remains the same. without the specificating coating, and the efficiency decreases significantly. So this shows you how efficiently you can really protect your perovskite material by passivating. I come very quickly onto the compositional engineering of perovskites. So you must have seen the composition of different cations. So here I highlight the presence of cesium. So the presence of cesium slightly shifts, blue shifts the emission maxima as well as absorption maxima. It's because of the different reasons, but I will discuss if somebody is interested. So let's consider the cesium is a very important component in the perovskite solar cells. Why it is very important? So now if you look at the SEM image, cross-sectional image microscope, so this is without any cesium, cesium 0 and cesium 5. You can clearly see the presence of microcrystal structure where the crystal are broken between that's a hole transporting material, electron transporting material. When cesium is 0, the crystal growth is not uniform. However, if you have a 5% of cesium, you can see the crystals are significantly grown, and there are blocks connecting between the ETL and the hole transporting material. So that's the beauty of having a 5% of cesium enhances the crystal growth. Not only the crystal growth is enhanced, but you have another important parameter which is influencing here. The perovskite is a very interesting material, but it also has a complicated structure formation. So when you start making the perovskite, it undergoes different morphologies. It's called typically polytypes. It's a delta phase, 4H phase, and 6H phase, and finally you get a three-dimensional perovskite. That's happening in absence of the cesium. However, if you have a 5% cesium or even 3% cesium, what happens, you eliminate all these unwanted roots, and then you go directly to your required perovskite. That's the beauty of the cesium. So the take-home message of my presentation is the presence of cesium is important to increase the crystal growth and as well as to eliminate unwanted polytypes formation, then followed by growth of the three-dimensional perovskite. So another interesting compound, so let me just come back to the cation. So this is methylammonium cation, formidinium cation, guanidinium. So let me give you the logic why we are working on this type of cation. So if you take the methylammonium, so you have a NH2, and this amino groups interact with your perovskite iodides. In other words, my goodness, I'm sorry for this. So the increased hydrogen bonding is very important. From methylammonium to formidinium, you have a 2 NH2 groups. From formidinium, this is guanidinium, you have a 3 NH2 groups. So the number of NH2 groups enhances your hydrogen bonding, and that significantly should enhance your stability. That's the logic. So unfortunately, methylammonium is not very stable cation because it undergoes methylamine and the iodine release. So therefore, the formidinium is one of the chosen cation, but this one also is not very stable. It forms a delta phase. So by putting the guanidinium, you can overcome these problems, but the size of the cation is so big, and this comes above the tolerance factor. It will not form the cubic structure. So what we have done is we have combined the ratio of 25, this is a 1 cubic unit, you have a 75% of methylammonium and you have a 25% of guanidinium. By combining these different ratios of small cation and bigger cation, you can accommodate into the size, and that gives you efficiencies in the range of 20%, not very high. However, the beauty of this material is when you have a 25% of guanidinium, you can see the red line, it's extremely stable performance up to 1100 hours. So this was published in 2017, and having this 25% of guanidinium enhances stability significantly. That's what we call compositional engineering. I come back to another important problem of the perovskite. It has a hysteresis. Hysteresis is it's an ionic compound. You have a defects. So what we are trying to do is we are reducing these defects by incorporating ionic liquids in the perovskite. This is, for example, take this ionic liquid, we are incorporating into the perovskite bulk. So without going into the details, let me just take you to the final result. So here as a reference sample followed by 1%, 2%, 4%, the spectral changes are not that significant. It's not contributing anything to the spectral properties. However, if you look at the presence of lead iodide is characteristic at 12.4, and this peak we are reducing significantly by putting this ionic liquid. That's the only information you can get from the XRD. You take you're finishing? The time is over? Yeah, just let me finish this 2 slides and then I come back. So if you look at the ionic liquid, without ionic liquid and with ionic liquid, after 2 months at 50% humidity, you can see the presence, the color is decolorizing, and with ionic liquid, they are extremely stable. So this information you can get since we have in the ionic liquid as a fluoride, as a marker. So what is happening here, why they are very stable performing, and this is a reference sample where the presence of fluoride is characterized. And now we take 1 grain of the perovskite with this ionic liquid, we dig from the top to bottom, and you can see that at 0, you have a significant fluoride, and up to 25 nanometers, you see the presence of the fluoride cation. So the way we are explaining is by putting the ionic liquid inside the perovskite solution, you form a coating shell on the top of perovskite grain, and that gives you extremely stable performance and high efficiency. So with that one, I skip the last section, which is the whole transporting material. If organic chemists are there, I can explain them all these things, and then followed by I come back to the ETL layers and the conclusion. So what I have provided today is 3-dimensional and 2-dimensional perovskite is very important to enhance the stability. And now I have also given the cesium incorporation allows us to overcome all these unwanted phases, and then that gives you the required phase and also crystal growth. The guanidinium is enhancing the hydrogen bonding, and that enhances our stability of the perovskite materials. The hydrophobic ionic liquids is a new phenomena in the literature, so we are working on it, and the ionic liquids enhance their stability significantly. This is my the people who are working in on the perovskites. This is my group, and I will be happy to answer your questions.